Hello, Supriya. Can you hear me?
Ma'am, 1 minute, ma'am. I'm giving live 1 minute.
Okay.
Good afternoon. Good afternoon, everyone. I am Supriya Naika, your host for this session of episode Creative Weekend Talk of episode 168. Those who are new to this platform, Creative is a registered trust and the group of people who are eager to gain new knowledge. Our tagline, Knowledge Square, sharing knowledge increases our knowledge, reflects our commitment to collective learning and growth. Our vision is to build constructive thinking across various domains by focusing on non-textual, non-academic, non-syllabus related concepts. Creative provide a platform for subject experts to share their insights, experience, and knowledge. Every Saturday from 3 to 4 p.m., we organize online talks on Zoom and live stream them on our YouTube channel, Creative GBD. Today's topic is insights into coronal mass ejection onset from 5,303 angstrom emission line observation with VELC and ADITYA-L1. This session will explore groundbreaking research in solar physics focusing on the ADITYA-L1 mission. We are honored to have Dr. V. Muthupriyal as our guest speaker. With her expertise, we look forward to an enlightening session on this fascinating subject. I welcome you, ma'am. I call Uma Devi, Creative Volunteer, to introduce today's speaker. Over to Uma Devi.
Thank you, ma'am. A very good afternoon to everyone present here. It is indeed a great pleasure to extend a warm welcome on behalf of Creative team conducting webinar on insights into coronal mass ejection, the Anstorm emission line observation with VELC ADITYA-L1 by a resource person, Dr. V. Muthupriyal, ma'am. Ma'am pursues a profession of project scientist in the data pipeline team for VELC payload on board in ADITYA-L1 satellite. Ma'am has pursued her PhD from Indian Institute of Astrophysics and Bharatiyar University, Tamil Nadu. She has ample interest in research including atmospheric physics, space weather analysis, technical expertise including statistical analysis, solar data visualization, forecast evaluation. Earlier, she worked as scientist in digitalization project IIA Kodaikanal and as junior research fellow in ISRO for Chandrayaan-1. With a great geniality, she published 23 research publications and 222 citations, which includes determination of the chromospheric quiet network element area index and its variation during 2008 to 2011. Digitalized archive of the Kodaikanal white light image representative result in 2013. Polar network index as a magnetic proxy for the solar cycle studies in 2014. Chromospheric variations with solar cycle phase using imaging and spectroscopic studies in 2015. Calibration of VELC detectors on board ADITYA-L1 mission in 2024. Data processing of visible emission line coronography on board ADITYA-L1 in 2024 and many more. Our ecstatic and enthusiastic guest has been hold gold medal for 2 times in MSc and MPhil for her outstanding performance. Cheers to you, ma'am, and once again welcome you, ma'am. I extend my welcome to Srinath sir, who has been the backbone of this program. Supriya ma'am, and all the participants in this webinar. Over to you, ma'am.
Thank you, Uma Devi. Over to you, ma'am. You can hand over.
Good afternoon, everyone. Can I switch on my video?
Yes, ma'am. Sure.
Okay. Is it visible?
Yes, ma'am.
Good afternoon, everyone. Thank you for being here today. And thank you, Srinath and Supriya, for inviting me and made this wonderful webinar. And I'm currently working with Indian Institute of Astrophysics in the data pipeline development and analysis of VLC data. VLC is the visible emission line coronagraph, which is a main payload in the ADITYA-L1. As you all know that ADITYA-L1 is the first Indian solar space-based solar observatory, and VLC is one of the prime payload in ADITYA-L1. So I'm involved in the development of data pipeline and analysis, and today I'm excited to share our recent result which we obtained from the VLC data. And please feel free to ask any questions at any point. I look forward to an engaging discussion. Let me share my screen. Hope screen is visible.
Yes, ma'am.
Yeah. So before getting into the results which we obtained from the VLC data, first let us have some introduction about our solar system and about our sun. So in the universe, we have a lot of super clusters, and in that one among the local group which where we have our Milky Way galaxy, and Milky Way galaxy has a lot of solar systems, and we are in one of the solar system where sun is at the center and we have planets around Earth, and we are at Earth, which is one of the planet in our solar system. And Milky Way galaxy, if you see the diameter of Milky Way galaxy, it is about 27 kilopascal. 1 Pascal is about 3.26 light years. Light year means it's a distance traveled by a light in 1 year. So if you imagine, if you travel up and down from North India to South India through air for 500 crore times, then only you can achieve 1 Pascal distance. So like that, Milky Way galaxy diameter is about 27 kilopascal. So imagine how huge it is. And in our solar system, sun is the primary thing. So why do we study the sun? It is very, very essential to know about the sun to lead a life on earth and to understand the various branches of physics. In sun is the unmanned laboratory, because we can understand about various branches of the sun like thermodynamics, plasma physics, and various atomic physics, nuclear physics. So all such physics can be explored by the one source, which is the sun. It's an unmanned natural laboratory which is used to uh, understand about other stars also. It is a nearby star. It is the only star which we can resolve to a greater extent. So through which we can understand about our other stars also. And it is very essential to understand its effect being on Earth to know about the effects, its effect on our Earth atmosphere. And this is about structure of the sun. Sun is not a solid ball kind of thing. It is in a plasma state, and it has several layers. First, inner core layer, which we call it as a core of the sun, where nuclear fusion reaction is taking place, where hydrogen atoms combine to form a helium and energy is getting generated. And this energy is getting transferred to the outer layer, which we call it as a photosphere. And within photosphere and core, there are two more layers, which we call as a radiative zone and convective zone. Then outermost layer is the photospheric layer, which is the layer we are seeing in the every day-to-day life in the sky. And above photosphere, there are two more layers, which we call it as chromosphere and corona. Chromosphere and corona is a very faint and less dense region compared to the photosphere. This photosphere layer, which we call it as a sun disk, and this chromosphere corona is a very less dense layer. So it will not be visible in the everyday day-to-day sun. But to observe chromosphere and corona, we can observe through the total solar eclipse, where moon occurs between Earth and the sun. So the sun disk will be occulted by the moon, and the outermost layer, which we call it as chromosphere, and corona can be visible. So to study about corona and chromosphere, we have to study only when the total solar eclipse is happening. And one unique science mystery, which we are even now, it is an unresolvable question, is why the temperature starts rising from the chromosphere and reaches to about million Kelvin in the coronal layer. See, if you are in Earth itself, if you see, if you are going in the various heights towards the sky, what we feel is a very chillness. The temperature will get reduced. But from the core, where the energy is getting generated, in the core, the temperature is about 15 million degree Kelvin. So once it reaches the radiative zone, convective zone, it gradually reduces. And once it reaches the photosphere, the temperature of the photosphere is about 5000 Kelvin. But when you see the suddenly, which we call it as a transition region, that is the layer between photosphere and the chromosphere, chromosphere and the corona, where you see the temperature suddenly shoots up. From the photosphere to chromosphere, it gradually increases to 10,000 Kelvin. But after transition region, coronal layer reaches up to 1 to 2 million Kelvin. So this is still an unresolvable question, and why this sudden change in the increase in temperature from the chromosphere to the corona. And let us have some glimpse about sun's active regions. This is the photosphere, which is the solar sun disk outer cover, that we call it as a photosphere. And if you see this black spots on the sun disk, this we call it as a sunspots. How these sunspots are getting generated? These sunspots are the primary active regions. So to know, we should know about the sunspot to study about how active the sun is. The sunspot is electrically generated by the electrically charged hot plasma. As I said, sun is in a plasma state where it is everything in ions. So these ions will move and it generates the magnetic field. So sunspots are the dark spot hole-like region where this magnetic field line from the inner layer, that is from the radiate convective zone, the magnetic field is getting generated, and this magnetic field line will peep out to the photosphere through this region. This we call it as a sunspot. How this magnetic field lines is getting peeped out? That is because of solar differential rotation. As I said, it is in a plasma state and it's not like a solid rigid ball. But within radiative zone, that sun is rotated at a uniform speed. But once if you come to the convective zone, the sun starts rotating differentially. Differentially means the equatorial region of the sun rotates faster and the polar region of the sun rotates slower. So this difference in the speed between equator and the pole makes the magnetic field lines getting twisted, tangled, and at one stage, when the magnetic field lines get twisted and it peeps through the from the inner layer of the sun to the outermost layer through these sunspots. This is how sunspots are getting formed in the photospheric region. And this as you all know, from the magnet we have two poles, north and south pole. Same way sunspot also have its a magnetic field line. So once one end will be called as a south and another end will called as a north. And the temperature of these sunspots is about 4000 Kelvin, which is lesser than the surrounding. The surrounding temperature of the photosphere is about 5800 Kelvin. So it appears darker. it is relatively cooler than the surface, so it appears darker, and this we call it as a dark spots or sunspots. So this I already explained. It's the differential rotation of the sun. Here, since equator rotates faster compared to the pole, so this magnetic field lines which flows from the north to south of the sun, it's getting twisted up, tangled. At one stage, it will come out through the to the surface of the photosphere. And in sunspot, we call it as a 11-year cycle and 22-year cycle. What does it mean? This 11-year and 22-year represents the sun's activity cycle. The solar cycle is a cycle that sun's magnetic field goes through approximately every 11 years. In the previous slide, I showed that there is a magnetic south and north pole. So in the first 11 years, if you see this left hand picture, that south is in the left side and north is in the right side. In the next 11 years, this north will come left side and south will come right. So this polarity reversal will happen every 11 years. And in the next, after 22 years, again it will revert back to the same. So this we call it as a 11-year cycle and 22-year cycle. And how it is happen in the sun, still it is in the understanding stage. So every 11 years, the sun's magnetic field completely flips. North will become south and south will become magnetic. The magnetic field poles will flip. Then it takes another 11 years to revert back to again same polarity. That we call it as a 22 years magnetic cycle. And this solar cycle affects activity on the surface of the sun, such as sunspot. And as the magnetic field changes, this amount of activity also will change. This is the number of sunspots that formed on the sun. It's plotted against the year. If you see from 1915 to 2000, it is plotted. That number of sunspot formation is changing. In the first 11 years, it reaches up to 120. If you see around 1958, it goes up to 240. So this number of sunspots represents the sun is very active in that 11 year. That is more number of magnetic activities, sunspots are generated. So this is the example for it. And if you see in the 11 years, it's not a constant number. First 5 years, it goes to increase, and at the 5th year, it will reach the maximum 5 to 6 years. Then it will start reducing the activity. So this is the 11-year sunspot cycle. So first 5 years it will rise and then decline. And now we are at the maximum phase. So ADITYA-L1 will provide us a very good activity. Sun will provide a very good activity. So ADITYA will be able to capture all such magnetic events. This is about Halley magnetic polarity law. As I said, that north and south pole, every 11 years it will flip, and after 22 years it will revert back to the original polarity. This Halley has found in 1999 that preceding and following sunspots are of opposite polarity, and after 22 years it will revert back to the same polarity that Halley found. So this we call it as a Halley magnetic polarity law. And this is a butterfly diagram. This in this picture, the lower panel I showed in the previous slide itself, which represents the number of activity, the number of sunspot against 11 years. And if you see, in the first 5 years, it increased and decreased. In the same way, if you see the top right, when the magnetic activity starts on the sun, it starts around 30 to 40 degree latitude. Then when it reaches to the minimum, it reaches to the equator. So it forms almost like a butterfly like shape. So this we call it as a butterfly diagram, where magnetic activity starts at higher latitude and then gradually it goes towards the equator. This is one such example for the differential rotation. Since the magnetic field lines are getting twisted because of differential rotation, these magnetic structures also dragged. from the high latitude to the lower latitude. This we call it as a butterfly diagram. And this is the image. This is the image from NASA Hathaway paper. But same image we have generated from our Kodaikanal observatory data also, where we have 100 years of photospheric and chromospheric observations. So from that we have also generated 100 years of butterfly diagram and the number of sunspot groups I plotted against years. And this we call it as a squirrel law. That is, sunspot starts appearing at 30 to 40 degree and gradually drift towards the equator as the solar cycle progresses. Then another is a tilt-Joyce law. In 1999, the scientist Joy, what he noted is the sunspot groups are tilted. Sunspot group means it's a north and south group. The leading spot close to the equator and the following spot is at an angle. So this tilt in the following spot and the leading spot, we call it as a tilt-Joyce law. And there are various studies are going on to study about the tilt angle against the solar cycle. So this tilt angle also varies with the solar cycles. So this is one of the important parameter to know about sun's activity and for predicting the sun's activity for the next 11 years, how it can be. And this is another finding from 1959, Babcock. He generated this magnetogram where you see that a blue line and yellow line represents the north and south fields of the sun. So it shows like a butterfly. And if you see at the polar region, first 11 years it is at yellow color, next 11 years it is at blue color. That is, this is north, then south. And if you see that after 22 years, again it comes back to the north. So these are the images which represents the 11 years sunspot cycle and 22 years magnetic cycle, which we call it as a polar field reversal. Now let us talk about solar flares and coronal mass ejections, which is the very massive event that happens on the sun. Solar flare is a sudden, intense eruption of electromagnetic radiation from the sun. The sunspot, whatever I showed in the previous slide, is the sunspots that represents the activity, that is magnetic field activity generating on the sun. And the solar flare is such a when the magnetic field lines are so strong enough, it will break and it will emit a sudden intense rise of electromagnetic radiation. So it is from one among the solar activity, sunspot. But if the activity is more, it will release sudden increase in the electromagnetic radiation, that we call it as a solar flares. Flares are classified as A, B, C, M and X class flare depending on its intense, how intense it is. X class flare is the most powerful flare, which has the peak flex of 10 power 0 10 power 1 watt per square meter. And this number of flares also increases with the number of sunspots. So study about the sunspot is more important to know about the sun's activity. And if sunspots are more on the sun, so obviously we can expect more number of flares and more number of CMEs can erupt from the sun. And this can cause major disruption to the power grids, communication networks, all our GPS systems, satellite, everything. So it's very important to understand and to know about flares. And next is coronal mass ejections, that we call it as a CME. The CME is a sun bursts with the power of 20 million nuclear bombs. If 20 million nuclear bombs are blasted, how much massive event it is, that much is the mass ejected from the coronal mass ejection. So it's a very big massive event that can happen on the sun active region, that is maximum on the solar maximum. So during a CME, enormous bubbles of superheated gas, which is called as a plasma, are ejected from the sun. And underlying cause, how the CMEs are getting formed, it is not well understood, but we should know about the CME, when it is happening, and in what direction it is traveling, whether it will travel towards Earth or whether it is going to hit the Earth. So these informations we should know in prior to protect ourselves from such massive event from the sun. So when the magnetic field twists too much and this hinge snaps the magnetic field and drive vast amount of plasma into the space. This plasma is nothing but a combination of protons and electrons. So that we call it as a solar wind that carries on the interstellar medium. So now let us talk about solar activity and how it is connected with the space weather. And space weather refers to the condition on the sun and in the space environment that influence and reliability of spaceborne and ground-based technical systems. So it can endanger our human life for astronauts and satellites and power grids on Earth and even aircraft operations, and it can change our climatic conditions also. So it is important to know about CME and activity happening on the sun. So when the CME impacts on the Earth, that very high cloud of plasma, magnetized plasma, blast out of the sun, as the CME can affect the Earth atmosphere. By distorting our magnetic field, we have a protective shield around the Earth. So when it is getting distorted by such massive events, it produces a aurora kind of thing. If you see in the sky, sometimes you'll see a colorful features regions on the sky. That is mainly due to the interaction of the CME particles which is ejected from the sun and from the earth magnetic field. So when it is interacting with the earth magnetic field, we could see such colorful aurora, and if it is very powerful event, it can break through our magnetic field and it can affect our earth atmosphere, satellite, power grid, as I discussed in the previous. This already I have covered. And such a significant geomagnetic storm, it recently occurred on August 12th, 2024. But luckily, it didn't impact a major impacts on our satellites communication systems. But we understood that it leads to the satellite drag. That means satellite where we are pointing the satellite, there is a drag in the satellite. So we have to make a pointing adjustments to bring it back to the position of the satellite. And these are some of the activity. Major solar activity affects the sun. In 1991, it affects the GOES satellite. 1994, Dutch Telecom. 1996, Telesat Canada. So these are the satellites which are affected by the CMEs. And recently in May 2024, severe geomagnetic storm. Elon Musk has announced that his Starlink satellites are affected by this on May 14. And from VLC data also, and from other satellites, other instruments which is on board ADITYA-L1 also captured such a massive event. And this is the solar activity, how it is connected to the terrestrial climate. One minute. And solar cycle related variations are evident in the terrestrial temperature. If you see here, this is the sunspot number of sunspots that is generated on the sun from 1600 to 2000. Here if you see, there is no sunspots are generated, almost nil in the sun. That we call it as a very sun quiet phase, that is Maunder minimum. Maunder has discovered this. So this period we call it as a Maunder minimum period. Almost for 60 years there was no activity on the sun. After that, it started appearing. If you see this kind of cyclic pattern is the 11-year solar cycle. It starts increasing, and the 5th, 6th year it will become maximum, then it will drop down. So this 11 years continues, and this 11-year activity also varies with years. It's not a constant, it's a variation. If you see in general, this number of sunspot formation on the sun is gradually increasing, and around 2000 it reached around 200 sunspot number. And this right hand side we have plotted the temperature, that is earth temperature. If you see, the temperature has increased almost 1 degree Celsius overall temperature. So the sunspot activity, that is solar activity, is very much it's evident in the terrestrial temperature record. So it's very important to know about the activity on the sun. And there are unanswered questions about the sun. This solar activity impacts us in many ways, and big questions remain unanswered is how in the sunspot cycle produced, and how are flares and CMEs are initiated, and how are the solar corona become so hot, and how does solar activity impact our climate change. So these are still there are a lot of theories and studies are coming up, and still people are under study, but still there is no like concrete conclusions on these questions. Now let us start discussing about ADITYA-L1. ADITYA-L1 is India's first space-based solar observatory, and it has 7 payloads. First is VELC, Visible Emission Line Coronagraph. This one is the major payload, very big instrument. And the next is SOOT, and PAPA, magnetometer, SOLEX, Helios. So these are the instruments which are in ADITYA-L1. Since it has several payloads which has a complete study about photosphere, chromosphere, solar wind. So since it has a complete study about the sun, we call it as an observatory. And in our solar system, sun is at the center, and earth is orbiting around the sun, and there are 5 Lagrangian points, L1, L2, L3, L4, L5, and our ADITYA-L1 is orbiting at L1. L1 is the point which is in between sun and the earth. It is in the sun earth line. If you join the line from sun center to earth center, it is at the it is at the sun earth line, which we call it as L1. It is about 1.5 million kilometer from the earth. So we are going ahead, little ahead from the earth atmosphere, and our ADITYA-L1 is orbiting at the L1. Since it is ahead from the earth atmosphere, we can have a 24 hours of observations without interruption of day and night. So 24/7 we can observe the sun. This is one of the major advantage of ADITYA-L1. And these are about the payloads and its capabilities. Visible emission line coronagraph is designed to study about the corona, which I said corona can be studied only only during the total solar eclipse times, or some ground-based observations are there. But since it is a very less dense and very less intense, we should have a very unified instrument to capture such a faint light from the earth. So it's very difficult. Sky should be extremely clear. There should not be any disturbance in the sky, clouds or something. Then only we can able to get this signal on the ground. So in the space based, this problem will not be there. So we can observe this faint signal from the space based for 24/7. So VLC is designed for this, and VLC has 4 channels, 3 spectroscopy channels and 1 imaging channel. Imaging channel will give you the topology of this coronal mass ejections and coronal loops informations, but spectroscopy will give you the more details about this physical properties, what's happening on the corona, how this CME is onset time, and how it is how it is sorry, how what is the onset time, and what are the implications, what's its Doppler velocity, what is the emission line full width of max. So these physical properties of the coronal structures can be studied from the spectroscopy data. And solar ultraviolet imaging telescope, which is a suit that gives information about the photosphere and the chromosphere. This is the imaging channel. It has a 11 filters which observe at 11 different wavelengths of this photosphere and chromosphere. Then Solex, Helios, Aspects, Papa, these all to study about the solar wind parameters. And to study about the magnetic field structures, there is a instrument called magnetometer. So these 7 payloads are on board in the ADITYA-L1. So as I said, to observe the solar corona, we have to wait till total solar eclipse, where moon occurs the sun. Then the solar disk will be occulted by the moon. Then the outermost layer can be visible from the earth. That is called as the coronal layer. And it lasts only for very few minutes. So for 24 hours continuous observations, we need a space-based observatory. Thus, we went to space. And visible emission line coronagraph, it's a artificial eclipse. In natural eclipse, that moon will occult the sun. Here, what we are generating the artificial eclipse, solar eclipse. We have a hole in the mirror where the sun disk light will pass through the hole and it will eject into the space, and the remaining light outside the solar disk, outside the photosphere, which is the coronal layer, that will be imaged and spectroscopically studied by our VLC. And VLC, we are studying about 3 solar radii. The solar disk, which is the photosphere, that we call it as a 1 solar radii. The radius of the sun disk, it's called as 1 solar radii. And from the VLC, we are observing from 1.05 solar radii to 1.5 solar radii in the spectroscopy channel, and 1.05 to 3 solar radii in the imaging channel. And one of the major advantage of VLC is there is no other payload in the world which can give the information from 1.05 to 1.5 or 3, which is the crucial region of the sun where the CME is getting lift off. So these informations can be measured from the visible emission line coronagraph, and for 24 hours. So no other instruments in the world is providing this data. So this is the uniqueness of our VLC data. And this is the optical layout of VLC. You see such a complex payload. It has some 40 assemblies of optical elements and all the 4 channels. This is the continuum imaging channel, and these 3 are the spectroscopic channel, and all these optical components are fixed in the box. So it's a very complex payload, and it needs obviously, as I said, corona is a very faint signal. To observe from the earth, we need to have a very clear sky without any clouds or something. But even in a space, we should have a very less scatter. This instrument itself will have a scatter light. So with the very less scatter, we can measure the good coronal signal of VLC. So the scatter of this instrument also, we should keep it in mind that it needs to be very, very less to study about the to get the coronal signal. And these are some of the payload integration photos which we have. IEA, Indian Institute of Astrophysics, has designed this VLC instrument, and the components are supplied by the ISRO. And this integration is happened at the Crest campus, which is one of the campus of IIA. So these are some of the images while integrating our payload. We have a thermovac lab over there, and this is the final satellite. This is the final VLC payload, which has all the optical elements, everything in that. And this is the finally packed stage before we send it to the ISRO for putting into the rocket. This is the final payload photo. And these are some of the facilities which we have it as a MGK main and laboratory at Crest campus. This is for testing the detectors and for environmental test. Here we used to test that vibration test everything here in MGK main. So these are the facilities which are available in our IEA campus. And these are the smart racks for VLC POC, that is Payload Operation Center, where we'll receive the satellite data. The satellite data, VLC data is downloaded at ISRO ISSDC. From ISSDC, they will transfer the data to us, that we call it as a VLC POC, Payload Operation Center. These are the racks where we get the data, and we have some computing servers to analyze the data. So the data which is downloaded from the instrument, from the satellite, it will be a raw data. It will be like binary data. So with the binary data, users cannot get any information. So POC center facility will generate the level 1 and level 2 data products, which we convert raw data to the scientific usable data. And we'll also generate some images, videos also for public outreach. So these are the main activities that is going on in the data pipeline. Now let me tell about some first science result which we obtained from our VLC ADITYA-L1. This is our article, that is new results on the onset of coronal mass ejections from 5303 angstrom emission line observation with VLC ADITYA-L1. And this was published in the Astrophysical Journal. And Professor R. Ramesh is the PA of our VLC payload, and myself and Jagdev Singh, who is the founder of this VLC payload. And it was published in Astrophysical Journal later in 2024, November 20. This is an open access paper. You can download and you can read it. Okay, first, before getting into this result, first let us know about what is this spectroscopy observation means. VLC has three spectroscopy channel. One measured at the wavelength of 5303, that we call it as a green line channel. 5303 corresponds to green color, so green line channel. And we have another spectroscopy channel, that is 7892, which we call it as a red channel. And next is IR channel, 10747 angstrom. So these are the three spectroscopic observations available from the VLC. If you see here, as I said, this is the occulter. We are making this solar disk light to go through the occulter into the space. Since our interest is to study about the corona, we are leaving this solar disk light into the space. And this white circle is the region of interest. And this is from 1.05 to 1.5 solar radii. Solar disk radius is 1 or not. So 1.05 to 1.5 solar radii is the field of view interest in the spectroscopic channels. This red color vertical lines are the slits. 1, 2, 3, 4. Another major advantage of the spectroscopic channel is it is a multi-slit spectroscopy, 4-slit spectroscopy. That means at a time you can measure, you can study about the region here and here and here and here. At the same time, you can retrieve the spectroscopic information at the 4 different regions of the sun. So this is the next advantage of this multi-slit spectroscopy. And each slit, we can move the slits also. That means, slit is fixed. We can move the images, so that image will move across the slit, and we can scan. This first slit will scan about 0.75 solar radii. Second slit we scan about 0.75. Third slit 0.75 solar radii. Fourth slit. So in this way, we will cover full 1.3 solar radii plus or minus 1.5 solar radii. So each slit can scan the sun image of 0.75 solar radii. If you park the slit at the same position, that we call it as a sit and stare observations. If you are scanning the images to get full minus 1.5 to plus 1.5 solar a day, that we are calling as a raster scan observation. So in the spectroscopic channel, there are two different modes. One is sit and stare mode, next is raster scan mode. Sit and stare mode is nothing but slit will be parked at one region of the sun. That is, slit is not moved, image is not moved, slit will always observe the same region of the sun. If it is in raster scan mode, the image will move across the slits so that we will get full image of the sun. So these two data, every day we are observing it from the VLC, and this is the spectra we get. It will come as a raw data, and the VLC POC we are converting into FITS data, scientific usable data, and this is the data. If you see, this is the first slit, second slit, third slit, fourth slit, and this is the occulter. That's why second slit and third slit is getting cut. This light will go through the occulter. And if you take one row profile of any one slit, profile will be looks like this. This is the profile. This is in the wavelength scale, and this is in the spatial scale. If you see these dips are called absorption lines, and this is the emission line. If you see, if you know normally spectra will have absorption line and emission line. So these are the absorption lines, and our 5303 is the emission line of the corona. This emission line, that amplitude of the emission line and the width of the emission line and the location of the emission line where it forms. This will give you the information about coronal intensity, its full width of maximum, and where it moves, the Doppler velocity. This movement in the peak location will give you about the Doppler velocity, whether it is redshifted or blue shifted. So from the information of this emission line intensity, we can derive these three parameters to know about the structure of the solar activity. And this is our first result from VLC. This is the sit and stare observations. As I said, slit will be parked at one stable position and image is not moved. So for 12:30 UT to 22 to 30 UT, we have parked the slit at one position, that is exactly at the limb of the sun. That is at 1.05 R0. We placed our slit and we wanted to study about what is happening very close to the limb, because such information is not available from any of the instruments in the world. So we wanted to know what is happening at 1.05 R0, very close to the sun. So what surprising result we observed is, here we had a high intense activity. Suddenly there is a dimming. This we call it as a coronal dimming event. This paper is mainly on the study about the coronal dimming event. Dimming is nothing but there is a region of high intensity. Suddenly the intensity drops out. So this tells us that some high activity structures is getting formed here and suddenly it is dropped. What we observed is, this is a coronal mass ejection. So when energy is getting built up in the magnetic field, that is a large number of ions, the energy density is getting built up. So once it reaches the maximum building phase, the CME lift off, that is magnetic field lines breaks out and CME is getting lift off. So this is the time where it got lift off from the surface of the sun, and all the materials which are on the surrounding plasma is washed out by the CME to the interstellar medium. So this is one of the major new result, where we are getting the onset time of the CME. At what time CME is getting lift off from the sun. And if you see the time profile, this is the image of the sit and stare, time versus position angle. If you see here, there is a sudden drop in the density. At the same time, as I said in the previous slide, from the emission peak, we can get the emission peak intensity, its full width of maximum, the width of the emission line, and the position of the emission line where it formed. So these three informations are plotted here. This is intensity, this is emission line width, and this is Doppler velocity. Intensity, if you see, there is a sudden drop in the intensity at 1318 UT, and corresponding full width of maximum, that emission line width, and Doppler velocity, it's increasing, that width of the emission line increase. What it tells is, since the width of the emission line is getting increased, broadened, that means the temperature of the surrounding plasma is increased. So that's what it conveys us. From the width of the emission line, we can study about the temperature, coronal temperature of the plasma. So from this, we got the Doppler temperature information and the Doppler velocity. This gives you information in which direction CME is progressing, whether it is towards the Earth. This is the line of sight component. So it is coming, whether it is coming towards us or whether it is going away from us. So these information can we get from the Doppler velocity. So these three important information we got it from this observation, this coronal dimming event, and this is the onset time, and it gives talks about the temperature of the surrounding plasma, and it is redshifted. Redshifted means it is moving away from us. It is not coming towards us. It is moving away from us. So these three information we got from the VLC data. This is the raster scan image. In the previous slide, what I showed is the sit and stare image where we placed a slit at one position. This is the image when we scan the image. This is the image of the fourth slit. I've shown only the fourth slit. We have four slits, right? So this is the fourth slit image where we can scan. If you see here, this is the occulter, and we have placed our slit exactly at the 1.05 R0 near the limb. And if you see here, before our sit and stare observation, there is a lot of coronal loops. This we call it as a coronal loops. If you see that there is a bigger coronal loop till 1.5 R0 we observed. But after that CME lift off, see here that coronal loop structure is completely disappeared and new structures are getting generated, and you can see clearly this difference in this picture. The loop structure which was there here, it's disappeared. So this is because of CME. After CME, these loop structures are vanished and new structures are getting regenerated. And this for LASCO C2 observations. LASCO is the coronagraph which is on board a SOGO satellite. In 1995, NASA has launched it. It also has the coronagraph, but its field of view starts from only 2.2 solar radii. Our starts from 1.05 solar radii. We are going very close to the sun, but C2 has the field of view starts from 2.2 solar radii to 6 solar radii. So they got the CME information only at 1348 UT, where we got the information at 1318 UT itself. So this is the importance of our VLC observation, that we can get the correct onset time. See here, they have measured at 1348 and they started collecting its high time plots with respect to solar radii. So these are the data points. They got it and they have done the quadratic fit and they measured it. 1354 UT can be the onset time of the CME, but which is not. From our observations, we got it as 1318 UT. So this extrapolation technique, which LASCO observations catalogs are following, may not give the real onset time. So VLC is giving the real onset time of the CME. And since it is spectroscopic observations, we are getting onset, not only the onset time, it's temperature, coronal temperature information and Doppler velocity information, whether it is coming towards us or away from us. This LASCO observations is an imaging channel, so it won't give such informations. So these are the importance of VLC, what we published recently, and it is getting a lot of citations and much more in results. We are writing, we are measured, and so nice results are coming up, and we are writing so many articles. So hope you will be see much more articles on this. Thank you. Please ask any questions if it is there.
Thank you, ma'am, and congratulations for the new data.
Thank you.
It's a very neat and clear presentation, ma'am. Very detailed presentation.
Thank you.
Now, question time. Any questions, you can unmute yourself and you can ask directly. We have questions in chat box.
Yeah, sure, please.
Can I read it, ma'am?
1 second. I can show. I can see. First is I have an elementary knowledge on this. Kindly explain how the magnetic field and their strengths are measured. These coronal structures from the VLC, we are seeing the coronal structures. I showed no coronal loops or even sunspots. Sunspots are the activity from the photosphere. Because of the sun's activity magnetic field only, we are getting this 11-year solar cycle. So this is the indirect measurements to know about the solar activity, that magnetic field generation, and how it is affecting the CME flares. All such solar activities because of this magnetic field generation on the sun. So these are the techniques which we are following it to understand about the magnetic field and the strengths. And what is coronal mass ejections? How does it impact space weather? I already covered in my slides what is coronal mass ejections, and it will impact much. Coronal mass ejection speed will varies from 300 kilometer to 3000 kilometer per second. So depending on the speed of the coronal mass, whether it is slow CME or medium or fast CME, it will affect our Earth magnetic field, satellites, communications, everything. So these are the impacts on our space weather. And how does the VLC visible line coronagraph instrument on board ADITYA-L1 contribute to CME research? This recent slide I explained that we are measuring the CME lift-off time, that is onset time, very accurately, where no other instruments has that facility to measure the CME lift-off time. So VLC is one among that, and along with that, we are getting the information about CME. This Doppler velocity and the temperature of the corona. So these three informations are getting three informations we are collectively getting from the VLC. So this is the uniqueness. What is the new program going on in ISRO? That I think Srinath can answer. New program, what is going on in ISRO? And what insights can be gained from observing CME onset using VLC, and how do these insights advance our understanding of our solar physics? Nice question. This CME onset time, it's very important to know that if it whether it is how much, if it is a very fast CME, how much time will it take to reach our Earth? And from the Doppler velocity information, we can know that whether it is reaching towards the Earth. So this information will make us to alert our to preserve our satellite communications and to protect us. So this information is very important. And spectroscopically, CME information is no other data in the world is giving. Only imaging, as I showed, the LASCO is giving images about the CME liftoff from the 2.2 solar radii. But CME liftoff spectroscopically is no data is giving. So it's very important to know about this coronal temperature and Doppler and CME onset altogether. So this will give the very impact on our understanding on the solar physics. How the measured spectra emission line is so broad, whether it is due to the bandwidth of the detector. Now bandwidth is about 7 angstrom. Here I will tell you. This is a spectra. So our bandwidth is about 7 angstrom. Full width of maximum of our bandwidth is 7 angstrom. So this is, I have written in a pixel. Actually, it should be in the wavelength. So center at 5303, we can go 3.5 angstrom, 3.5 angstrom. We can cover this much wavelength from our spectra. And 5303 is the only emission spectra. And there are some other instruments which can give the spectra in the UV region. But the problem, uniqueness of this 5303 spectra and the UV spectra is UV spectra has a mixing of ions. There is this 5303 spectra corresponds to only iron 14 ion, which is existing in the sun's corona. But UV ion, there is a blending of ions. It may not it is not correspond to the one single ion, so it is a mixing of ion. So study about the coronal temperature from the one ion is very difficult in the UV studies. From this green line visible line, it corresponds to only one ion, so it's very easy to know about the coronal actual coronal temperature of the sun. I think that's all, Supriya.
One more, ma'am. Now, maybe
How
continuation.
do CME onset observations from VLC complement other space weather monitoring efforts? I covered it already. I think from the LASCO, I showed that CME informations can be got from the LASCO observation also, but that is from only 2.2 solar radii. So they are extrapolating it to estimate the onset time. That estimation time is 1354 UT. But see, from our real observations where we got sudden dimming, that is about 1318 UT. So this gives you information, exact information about the CME onset time. So it is important to know about how much time it will take to reach our Earth or something. So this onset time estimation is very crucial, important thing. So this is the complement from the other space weather. And it's a spectroscopy. That is another advantage.
Venkat,
Yes, thank you, ma'am, for letting me speak. This was a
Thank you.
great session on its own. So, you explained that there is a phase for entire solar activity that lasts 11 years.
Hmm.
I just wanted to ask, what is the life of one sunspot? So, one sunspot that forms and then it just dies and some other sunspot forms at a different location.
Yeah. Thanks. A very good question, Venkat. Thanks for your interest also. I'm
Thank you.
happy to see your interest. Hope you will be a future astronomer.
Okay, thank you, ma'am.
See, our sunspot is an activity which is formed, as I said, because of magnetic field getting tangled and it is paired up and it comes to the photosphere, right? At the same time, there is a differential rotation and rotation of the sun also. The sun rotates 2 kilometer per second. So, like Earth is rotating 24 hours, sun also rotates. So this sun rotates 2 kilometer per second, and so it is 13 degree per day. So it travels, sunspot, it travels and it goes for the far side of the sun, which we cannot visible. If it is comes to the front side, we can see, far side we cannot see. But generally sunspot leads up to few hours to few days.
Okay. And then another one will form at some other location.
Even few months also, the groups of sunspots can live even for few months. It
Okay.
depends on how active that magnetic field is, how strong the magnetic field is. If it is so strong, that can live for even few months also.
Okay. Got it.
Thank you.
Thank you.
any more questions? Okay. I think all clear. Thank you, ma'am, for the wonderful session. It's a really very neat session.
Thank you. Thanks for
Slowly,
Srinath and you for inviting and making it happen.
you gave a background details and all. It's very easy to understand the topic. Thank you very much, ma'am.
Thank
Thank
you.
you, one and all, for being with us. We are
Thank
ending.
you. Thank you.